In this video, we're going to look at the relationship between continuity and differentiability. And remember, continuity, okay, informally just means that there's no hole or vertical asymptote or jump in the graph. Differentiability just means that you are able to calculate the derivative at a given value of x. Okay, so that's what we mean by differentiability. Okay, now, remember that the derivative is slope of the tangent line, okay? So differentiability has an important graphical interpretation that we call local linearity. Okay, now local linearity just means if we, pick a point on the graph of a curve and we draw the tangent line, through that point, okay, if we were to zoom in on that point enough times, eventually you're not going to be able to tell the difference between the curve and the tangent line, okay? Or local linearity means given the graph of a function that is curved, if you pick a point on the curve and you zoom in enough times, it's eventually going to look like a line. Okay, so that's what we mean. Local meaning at a point, and linearity meaning if you zoom in enough times, the curve is eventually going to look linear. Okay? Now, in order for a function to be differentiable at a point, the function or the curve has to have this property, okay, of local linearity. All right, so that's how you could tell, if a function is differentiable at a point. If you zoom in on that point and eventually the graph looks like a line, then the function is differentiable at that point. Okay, just so you kind of see an example of a function that's not differentiable at a point, here we're looking at the graph of absolute value of x. And remember, that's one of our parent functions. The graph of absolute value of x looks like a V, okay? And so we're going to focus on the origin. Now, if, let's say, we zoom in on that part of the graph, no matter how many times we zoom in, okay, to that point, it is never going to look like a line, okay? Like there is still going to be a sharp corner there, no matter how many times we zoom in. So that means that the function absolute value of x is not differentiable at x equals 0, okay? So, or another way to think of this is the graph is not locally linear at x equals 0 because the corner does not disappear when we zoom in on the origin. Like it's never going to look like a line, all right? So the takeaway from this is that, f of x, which equals absolute value of x, is not differentiable at x equals 0. Okay, so that means you cannot calculate the derivative of that function when x equals 0. All right? Okay, so now that you guys kind of have an idea, what is required in order for a function to be differentiable at a point, okay, it has to have that property of local linearity. Let's look at some other examples where a function is not differentiable at a point. Okay, so these are the conditions where f prime of a, which is the derivative at a point, fails to exist. Okay, we already talked about the first one. So the first condition is when there is a sharp corner in the graph. Okay, and again, we're using absolute value of x as an example. There's a sharp corner at x equals 0. And so we would say here f prime of 0 does not exist. Okay, because there's a sharp corner. All right, the second condition is what we call a cusp. Now, honestly, a cusp is just like a special type of corner. Usually, the difference would be like a corner is created by lines and a cusp is created by curves. Okay, so this time we're looking at the graph of x to the 2/3 power, and the graph of the function looks like this. But again, there's, a sharp corner at x equals 0. More specifically, we call it a cusp. But f prime of 0 in this case does not exist. Again, because that graph does not have the property of being locally linear. Okay, like again, if we zoomed in on the origin, it's never going to look like a line. Okay. And you guys, I can show you that if we actually tried to calculate the derivative, well, we can calculate the derivative, okay? And we can find f prime of x. We can just use power rules for that. But look what happens if we try to plug in 0. We're going to get two-thirds times, okay, now remember, x to the negative 1/3, okay, is the same as 1 over x to the 1/3, okay? So if I plug in 0 for x, we're going to end up with 2 over 0, which is undefined, okay? So you can see, algebraically, why the derivative does not exist at 0, because if you tried to do power rule, you'll end up with 0 in the denominator. So, okay, but graphically you can tell because of the cusp or sharp corner in the graph. All right, a third case where the derivative does not exist is when we have a vertical tangent line. Now, I can tell you guys, these are a little bit harder to find or to see in a graph. So, for instance, right at x equals 0, if you draw your tangent line, it's actually going to be vertical. And because slope of a vertical line is, undefined, we would have to say that the derivative here is undefined or does not exist. So here we're saying f prime of 0 does not exist. And again, I can show you, if you tried it algebraically, let's say we find the derivative, cube root of x equals x to the 1/3 power. So if we did power rule, and then let's say we simplified, this would become 1 over 3 times the cubed root of x squared. If we try to plug in 0, again, notice we're going to get 0 in the denominator, All that is still going to equal 1 over 0, which is undefined, okay? So, algebraically, you're going to end up with 0 in the denominator, but graphically, what's happening graphically is that there is a vertical tangent line in the graph. Okay, so again, that would be another case where the derivative does not exist because derivative is slope. Slope of a vertical line is undefined or does not exist. Okay, now the fourth case would be at any discontinuity. Okay, so the graph here actually has a jump discontinuity at x equals 0. So again, we would say f prime of 0 does not exist, but this category is any discontinuity, not just a jump, okay? So if there's any kind of discontinuity, and remember our discontinuities are a point discontinuity, which is a hole in the graph, infinite discontinuity, which is a VA, vertical asymptote, or a jump in the graph. Okay, so if the function is not continuous at that x value, then you automatically know the function is not differentiable at that x value, all right? Okay, so you guys, Now that you know the cases where a derivative does not exist, okay, there's an important relationship between continuity and differentiability. And it works like this. If f is differentiable at a, then you know f is continuous at a. All right? Because we just said if there's a discontinuity, then the function is not differentiable at that point. So if you know the function is differentiable, then you can make the conclusion that the function is continuous at that point. But it doesn't work the other way around, okay? Continuity does not imply differentiability. You know, absolute value of x is an example. The graph of absolute value of x is continuous. There's no hole, there's no VA, there's no jump, you know, but absolute value of x is not differentiable at the sharp corner, all right? So anyway, you just have to make sure, you know, that you understand differentiability implies continuity, but continuity does not imply differentiability, okay? All right, now, let's look at some examples. That was the meat and potatoes of the lesson. Okay, so here we're given some graphs, and we want to identify the numbers or x values at which f is not differentiable. All right, so remember, we're looking for any of those four cases: a corner, a cusp, a vertical tangent line, or any discontinuity. All right, so let's look at graph 1. Well, I'm noticing there's a sharp corner at x equals -4. So this function is not differentiable at x equals -4, okay, because of the cusp. And then I'm noticing there's a jump discontinuity when x equals 0. Okay, so this function is not differentiable at x equals -4 because of the cusp, and also at x equals 0 because of the jump discontinuity. All right, let's go to graph number 2. All right, so this time, well, it's looking like there's a vertical asymptote at x equals 0. So I'm just going to call that an infinite discontinuity. All right, and then if I'm kind of scanning over my graph, well, there's also a cusp at x equals 3. And you guys, I mean, if you call it a corner or a cusp, you know, I wouldn't worry too much about, you know, those two. If you said x equals 3 because there's a sharp corner in the graph, that would be all right, honestly. All right, so let's look at graph number 3. All right, now, okay, it's easy to see, you know, the sharp corner or cusp at x equals 4. What is harder to see is that there actually is a vertical tangent line right here at x equals -1. Those are definitely harder to see. And I can tell you that on the AP exam, they usually will tell you in the question stem where there is a vertical tangent line. Okay, so they might say something like, the graph of f of x is shown above. There, you know, there is a vertical tangent line at x equals 2, and then they'll probably give you other information. But because those are harder to see graphically, you know, just given a graph, they usually have to tell you, you know, where the vertical tangent lines are. But you just need to remember that means the function is not differentiable at that point. Okay? All right, let's look at graph number 4. All right, so as we're scanning through this graph, we definitely have a jump discontinuity at x equals -1. And then we definitely have a sharp corner or cusp at x equals 2. So this function is not differentiable at either value. Okay, now we're going to get into some more like algebraic type problems. All right, so you guys, in order for a function to be differentiable at a value of x, two things must be true, okay? And let's just say we call, that value of x equals a. Okay, well, first of all, f of a has to be defined. And then the second thing is, remember that a derivative is a limit, okay? This is going back to the definition of the derivative as a limit, okay? If you guys remember our definition of one form of the definition of the derivative, and the easier form to use here is the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so that was one of our definitions of the derivative. Now, this is a two-sided limit. So what has to be true for the two-sided limit to exist? I hope you're thinking your one-sided limits have to be equal, okay? So the second thing that has to be true is that the limit as x approaches a from the left of f of x minus f of a all over x minus a has to equal the limit as x approaches a from the right of f of x minus f of a all over x minus a, okay? All right, so let's apply this now to the next example. Consider the function g of x, which equals the square root of x plus 1 when 0 is less than or equal to x and x is less than or equal to 3. And g of x equals 5 minus x when 3 is less than x and x is less than or equal to 5. Okay, is g of x differentiable at x equals 3? Show the complete analysis. All right, well, first of all, we just have to make sure that g of 3 is defined. Okay, so to find g of 3, because this is where x is equal to 3, we're going to plug in to the square root of x plus 1. And we get 2, okay, which means check, it passes number 1. G of 3 is defined. Okay. Number 2, we have to evaluate these one-sided limits. Okay, now, this would become the limit as x approaches 3 from the left, okay? So again, if x is approaching 3 from the left, we're looking for values less than 3. Okay, this again is where x is less than 3. So we're going to use this part of the piecewise function, and we're going to use our definition of the derivative. So this would become the square root of x plus 1, okay, because that's f of x, minus, well, g of x in this case, but anyway, okay, minus f of a, which in this case would be g of a. So we're just going to plug 3 into the square root of x plus 1, and we know that's going to equal 2, and that's going to be all over x minus 3. Okay, now, to evaluate this limit, if we try direct substitution, we get 0 over 0. But we could try multiplying by the conjugate over itself. Okay, so if we do that, then this is going to become the limit as x approaches 3 from the left of, okay, multiply straight across in your numerator, we're going to end up getting x plus 1 minus 4. Okay, all over, and then don't multiply out the denominator. We're just going to bring these two factors together. Okay, well, notice our numerator is going to simplify to x minus 3. So your x minus 3s are eventually going to simplify, leaving the 1 in the numerator. Okay, we're getting there, guys. So we now have the limit of 1 over the square root of x plus 1 plus 2, and I think we can now use direct substitution. And remember, that's when you can drop your limit notation. So we're going to plug in a 3. We'll end up getting 1 over 2 plus 2, which equals 1 over 4. Okay, so that's the limit from the left. Okay, now we got to evaluate the limit from the right. I'm going to do that in a different color. Okay, well, if we're approaching 3 from the right, okay, that's when x is greater than 3. So we're actually going to use the 5 minus x. Now, this limit is a lot easier to calculate because we can just do direct substitution and we get 2. Okay, now notice the one-sided limits are not the same. So this just failed number 2. This was a game show, you just got to All right, so our conclusion would be that g of x is not differentiable at x equals 3. Okay. Now, if we had, let's say that those limits ended up being equal, the left-hand limit equals the right-hand limit, then our conclusion would be that g of x is differentiable at x equals 3. Okay. All right. One last example, you guys. Sometimes you're going to be asked to find values that make the function differentiable. And in this case, we're going to go back to the idea that, first of all, the function has to be continuous, okay, for the function to be differentiable at x equals 1. And so let's say this question had been, you know, for what values of a and b is the function continuous at x equals 1? Remember, in order for the function to be continuous, the limit from the left, and we would be using 1, which is our cutoff point of f of x, has to equal f of 1, and that also has to equal the limit as x approaches 1 from the right. Okay. It just so happens in this example that, you know, because here it says x is less than or equal to 1, you know, that these values are going to be the same, because to evaluate both, you'd be plugging into the 3ax squared plus 2bx plus 1. Okay, so if you guys remember, the easy way to do this is to plug 1 in for x and then set the expressions equal to each other. Okay, so if we do that, we would end up with 3a, because, you know, 1 squared is 1, plus 2b plus 1 is going to equal a minus 4b minus 3. Okay, and again, I'm replacing all the x's with 1. Okay. All right, then I think I would put this in an easier form to deal with. I can tell you guys we're going to end up with a system of equations. So I think what I would do is move my a and b to the left side. So like I'm going to subtract the 1a from the 3a to get 2a. And then I'm going to add the 4b to the 2b to get 6b. And then I'm going to subtract the 1 from the negative 3 to get negative 4. Okay. All right. Now, this equation is based on continuity. All right, because the function has to be continuous, you know, in order for it to be differentiable. All right. Now, the next part of this is that in order for the function to be differentiable, the slope from the left has to equal the slope from the right. Okay. Now, you guys, what I'm going to do is I'm going to find the derivative of this piecewise function. Okay. All right. So we're just going to find the derivative of each piece separately. Now, the a and the b, those are constant, so you kind of just bring them along in your derivative. Okay. So derivative of 3ax squared using power rule would just be 6ax. Okay, plus derivative of 2bx is going to be just 2b. And derivative of 1 is 0. All right, now for my bottom piece, I'm going to find the derivative. And again, using power rule, I'm going to get 4 times a times x cubed minus, and then I'm going to get 8 times b times x, and then minus 3. Okay, now what we're going to do is kind of similar to what we did with the continuity. So for the function, to be differentiable, we have found the derivative of each piece. Now we're going to plug 1 in for x, and we're going to set those expressions equal to each other. Maybe I'll put this in a different color. Okay, so if I replace x with 1, I'm going to get 6a plus 2b equals, and then I'm going to plug 1 in for x in the second piece, so we'll get 4a minus 8b minus 3. Okay, then I'm going to do a similar thing just to try to get this a little bit more manageable. I'm going to subtract the 4a from the 6a to get 2a. I'm going to add the 8b to the 2b to get 10b equals, and I'm going to leave the negative 3 on the right side. Okay, now why did I do that? Because we now have a system of equations. All right, these are our 2 equations. One is based on continuity and one is based on differentiability. So now I can use my system of equations to solve for a and b. Okay, so I'm going to use the elimination method here, where this is where you add straight down and you want one of your variables to cancel. But I'm noticing right now, nothing's going to cancel. So I think I'm going to multiply my second equation by -1 and just like flip all these signs so that my 2 a's are going to cancel. Okay, but now I'm going to have 6b minus 10b, so that'll be -4b equals -4 plus 3, which is -1. Okay, divide by -4, and b equals 1/4. All right, so then what I can do is go back to either of the original 2 equations. I think I'll just go to the top one. And we're going to plug in 1/4 for b. And we will solve for a. Okay, so we'll end up with 2 times a, okay, plus 6/4, which we can make that 3/2. Okay, equals -4. All right, we'll subtract the 3/2 from the -4. I would find the common denominator, so making this -8/2. Okay, so we'll get 2a equals -8 minus 3 is -11/2. And then I'd probably just multiply by 1/2. And so we're going to get a equals -11/4. Okay, but we've done it. These are the values of a and b that make the function differentiable at x equals 1. Okay. All right, so just a quick recap of what I did there. You're going to set up one equation based on continuity. And so all I did there is I plugged in 1 for x in our original piecewise function and set the expressions equal to each other. And then your second equation is going to be based on differentiability. So we found the derivative of each piece, okay? And then I plugged in 1 for x and set the expressions equal to each other in the derivative. And then that gave us a system of equations, and so then we just solved the system using elimination. All right, so that concludes the video. We'll definitely practice this some more in class tomorrow. But as always, thank you for watching and have a good night.